Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master, Refat Bari. Watch his videos to achieve your dream.
Welcome to the 12th lecture in special relativity. And here's the idea. Our goal is to derive a formula for electric flux. We already did that in its integral form in our last lecture. Today I want to do the same thing but from a different perspective really. And that perspective is through the perspective of the four factors we need to consider when constructing the definition of electric flux. One of those factors I gave to you last time, which is flow. The flow, the speed, the velocity of the electric fields through some surface. Now I'm going to give you some time to go ahead and think about what the other three factors may be. Go ahead, good luck, and I'll see you in a few seconds. Alright folks, so hopefully that was enough time. I'm going to go ahead and write down the other three factors to consider and then we're going to discuss them. Okay, these are the four factors we must consider when constructing a definition for the electric flux. These four factors. Now, permit me some time to discuss these four factors. First and foremost, flow. Why is flow important? Well, it's just like if you have a boat on a river, right? The boat is going some direction, the current is pulling the boat in a different direction, right? And to find the direction of the current that directly affects you, you need to find a component of the current that is in your direction, right? In your direction. And of course, to do that, you have to take the dot product between the current and whatever direction you're going, right? So that's how we deal with flow. How about area? Area is a complex topic because we're dealing with variable surfaces here, right? They're not neat surfaces like rectangular prisms or spheres or cylinders. These are variable surfaces like a boat or some kind of a sheet of paper, right? So how do we deal with area? Well, we know how to deal with area. We chop up our surface into many small, tiny pieces that, well, eventually we'll refer to them as dA, right? So you can see I've chopped up my surface into many small, tiny pieces. How about density? Well, density is all about how close together are these electric field lines. And density really comes naturally as you integrate over your surface. So density is kind of going to be taken care of for us. Next we have angle, right? Angle, of course, I already told you guys how to deal with angle, and that's to take the dot product between the electric fields and whatever direction the unit normal vector is, right? So we know how to deal with all four of the factors, right? Flow, how do we deal with flow? Well, flow is going to be given by the function for the electric field itself, E, X, Y, Z. Area, we're going to take the slice and dice approach, which is going to be to chop up our surface. How about density? Well, density is going to really be taken care of for using the surface integral, right? Surface integral, right? And the angle, of course, angle is taken care of as we take the dot product between the electric field and our unit normal vector. So we have our four factors and the four ways we deal with our four factors, right? And this is really the key, the golden road to establishing the formula for the electric flux, right? These four key factors and their equally important solutions. Okay, now what's up next? Now I want to show you, now that we've already derived the formula for electric flux and you have a very thorough way of understanding the electric flux, I'm going to do like a 20 second quick dimensional analysis of the electric flux formula, just to give you a more holistic sense of what we're dealing with here. And that's going to be our lesson for today. So let's erase all of this and we'll be good to go. Okay, so let's do some dimensional analysis, right? What's the equation for electric flux? Why am I putting all my markers here when I should be dropping them in the bin, folks? Dropping them in the bin. Now, here's the formula for electric flux, right? We have the actual phi symbol phi sub E to represent electric flux, not some other type of flux, right? Is equal to the closed surface integral. The closed surface integral of what? The closed surface integral of the dot product, which we've been really bashing over, of the electric field and the normal unit normal vector, all times what we're actually integrating in respect to, which is a super small tiny piece of area. Okay? And of course this is Maxwell's first equation, Gauss's law of electric fields. That's the whole point of studying this. Now, let's do some dimensional analysis, right? Well, it's actually going to be pretty easy. The electric field is measured in what? Well, typically we measure it in volts, right? And what about our unit normal vector? Well, this is a unit normal vector. It's unitless, right? So it doesn't have any units. It has no units. And what about our area? Well, since we're dealing with surface area right here, right? And when you're talking about surface area, no matter what dimension you're in, what are you going to be talking about? You're going to be talking about square meters. Right? Who agrees with me? Give me a hand, folks, the live audience, if you agree with me. Okay, good. Hopefully I didn't make any mistakes here. Now, take some time to really consider this formula, right? Why does it have to be volt meter squared? Well, as I just showed you, the electric field measured in volts, the area measured in square meters. So the units for electric flux is simply going to be volts square meters. Okay, that's enough for electric flux. What do we have coming up next? Do we have 2 tips and tricks, or do we not want to reveal that to our audience? Well, let me reveal that to you anyway. What are our 2 tips and tricks? Well, to understand them, I'm going to take you through some examples of electric flux. Enough with definitions, now time for actual examples. Okay, so when talking about electric flux and presenting it to my students, I really like this example of the 3 Musketeers. Right, you have three kind of boxes right here. This is my first box. Here's my second box. And here's my third box. We're going to use these 3 boxes, aka my 3 Musketeers, to understand what electric flux tells us. Okay, first let's start off with our first box, right? First box, what am I going to show you? I'm going to show you, using this purple marker, some electric field lines penetrating through this box. I don't know if I actually want to draw it in full 3D. Just like that. We'll just drop these bad boys down and we are in the moment. Okay, so first box. What have we got? We got some electric fields coming in, coming out. Coming in, coming out. Coming in, coming out. I might have butchered the last one, but you get my point. I hope you do. So they enter the cube here and then they exit the cube on the other side. Now my question is simple. Now my question becomes super simple. What is the electric flux through this box? Let's pick a different marker. My friend, can I get the green marker, please?
That's actually kind of like dark.
Yeah, whatever. Okay. So tell me what the electric flux is right here. What's the electric flux right there for that box? Well, let's try to understand it, right? This one's actually pretty nice. I like this one. So we've got, what have we got? We've got the electric field lines coming in, right? They're coming in into the box. And what's the flux going to be? Well, it's going to be what? Is the region getting more dense or less dense? It's getting more dense, right? Region that's getting more dense is going to have negative flux, right? You can kind of think of there as being some kind of electron inside this box, and so the charges are coming in. The electric field lines are coming in. So there's going to be an inward negative flux right here. Inward negative flux, negative electric flux when we go in. But then after they come out, the surface is getting less dense, right? The electric fields are coming out, they're going away. That's going to mean an outward flux that's positive. An outward positive flux. Positive flux. How do I write positive flux? I'm going to just write plus and then the electric flux sign. So what happens is that the negative inwards electric flux is going to cancel out with the outwards positive electric flux. Negative inwards electric flux, positive outwards electric flux. That's going to give me a net flux of 0. Okay, so that gives us our first moral, our first tips and tricks when dealing with flux. When you're dealing with electric flux, you have to consider the net electric flux, right? You can break down your surface into however many pieces, but at the end of the day, it's all about the net electric flux. You have to sum up all your fluxes all over all your surface pieces, and that will give you your total flux. Okay, next one. What am I going to draw for this one? Well, I'm going to have the same electric field lines, right? 1, 2. But this time it's going to come with some manner of twist. Let's see if our students can deal with this one. So for this electric flux example, what I want to do is have some electric field lines kind of branching out. It's going to look kind of like a tree, which I know might look weird in the middle of our cube, but let's see what we can do. Let's see how we deal with this one. Okay, so our goal is to find the electric flux through this cube. And how are we going to do that? Well, the same philosophy applies, right? First and foremost, electric field lines that are going horizontally, these electric field lines, as I said, they're going to sum up to 0, right? There's an inwards right here on this kind of left-hand side of the cube. I'm going to have an inwards negative electric flux. So let's, how can I denote that? Let's get an orange marker right here. I've got a negative electric flux right there. Negative electric flux right there. And then I've got a positive electric flux coming out on the other side. So on my other side, I've got some kind of a positive electric flux. So I can go ahead and write that by just writing it down, right? So plus my positive electric flux. Okay, so those negative electric flux inwards is going to cancel out with my positive electric flux outwards. What about those coming out? Well, they're obviously not coming in, they're just branching out from inside of the cube. So what's going to happen is that these field lines are going to create positive flux, right? Because the region itself inside is getting less dense, right? So we're going to have a positive electric flux through this part of our cube, through this surface. Remember, we're not dealing with volume, folks. We're dealing with surface. So please try to keep that in mind, because even I messed that up when I first started. So this is going to give me some positive flux, because the electric field lines are branching out from the cube, right? They're starting from inside the cube and they're branching out. That's going to give me a positive flux because the surface right here is getting less dense, right? So my electric flux, this negative inwards flux is going to cancel out with this positive outwards flux. That's going to give me 0 right here, but then I'm going to still have a positive electric flux on the top. Okay, and likewise, I'm going to have a final scenario where instead of well, I'm going to have my good old, I think you can predict what I'm going to put for this one. Instead of having a Christmas tree branching out of my box, I'm going to have a Christmas tree branching into my box, something like this. I don't know if this actually looks like a black hole. Actually it does, now that I think of it that way. Okay, so what can we do here? Well, what we want to calculate, of course, is the total electric flux through this surface. How are we going to do that? Well, oops, let's erase that little mark. Now, how are we going to calculate the electric flux, net electric flux, through this surface? Well, what I can do is, once again, take the same philosophy. On the left-hand side, I'm going to have a net negative electric flux. On the right-hand side, I'm going to have a net positive electric flux, right? And those two are going to cancel out. So let's go ahead and write those down. I'm going to have a net negative electric flux on the left face of my cube. And I'm going to have a net positive electric flux on the right side of my cube. So plus. Okay, hopefully that's visible. Hopefully that makes sense. And finally, let's consider these branches actually coming into my cube. That's going to create a negative flux, right? So you can imagine some kind of a negative charge, some kind of an electron inside my cube. So that's going to create some net negative electric flux. So my total electric flux is simply going to be what? Well, if I add all of these up, negative, positive electric flux will give me 0. But then I have this negative net electric flux due to the branches coming in. Okay, folks, so hopefully that gave you, these 3 examples gave you some idea of how to qualitatively calculate electric flux. We're going to obviously do some computational examples soon. But yeah, hopefully that makes sense. 0 electric flux, positive electric flux, negative electric flux. 0 electric flux means garbage in, garbage out. What comes in has to come out. Any charge outside has to create 0 electric flux, as you've just seen. Whoops. Next up is positive electric flux, which happens when the surface area is getting less dense. So as you can see, these branches are kind of escaping our surface, so making it less dense. And finally, negative electric flux happens when a surface is getting more dense, right? So you can see these are really coming in, they're converging at some kind of a negative charge inside our box. Thank you for watching Special Relativity Lecture number 12. We'll see you next time.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.